Good morning, dear students. In the last video that we have discussed about the numerics when it comes to Young's double slit experiment, and hope you understand all the numerics. Before that, we have already discussed about the angular fringe with beta and angular fringe with theta, linear fringe with beta, everything that we have already discussed. Okay, and in similar way of Young's double slit experiment, now we are going to discuss about Young's single slit experiment. Okay, in this single slit experiment, how the light passes through the slit, and while passing, what are the natural phenomena which is happening over here, and thus these are all the things which we are going to discuss in the wave optics. Okay, let us go to the topic: diffraction, diffraction or diffraction. It is nothing but bending of the light in the edges. Okay, you should understand that diffraction or diffraction, it is considered as bending of the light in the edges. In the edges, the light will started bending and it will go as a wave. That is what diffraction or diffraction is called about. Okay, so how this diffraction is happening in Young single slit experiment, that is what we are going to discuss it. Okay, here the fringe pattern in single slit experiment, that is what the thing that we can see here, the fringe pattern in single slit experiment. It is similar that of a Young's double slit experiment. In Young double slit experiments, we can see two secondary sources, S1 and S2, or otherwise two slits that we can see over here. But in single slit experiment, you can see only one slit. So there is a light source. From there the waves are coming parallelly, and when it reaches the slits in the edges where the slits in the opening where the light penetrates, it will started moving in all directions. That is called bending of light, because we already studied that light will move in a straight line. But still, if a small opening is there, it is not captured only as a small hole. It is captured as a rays, a group of rays which is coming out from this small opening, so that the light is traveling all directions. Okay, straight line, but in all directions. So if we consider this is in a wave form, diffraction is happening. Okay, so diffraction and fringe pattern, how it is happening in the Young single slit experiment, we are going to see it here. So in diffraction, there is an incoming wave which passes through the single slit. Incoming wave, this is incoming wave, passes through the single slit. As a result, diffraction pattern was obtained on the screen. We are placing the screen as usual. We are doing it for Young double slit experiment. Similarly, here also a screen is there, but there we have seen that a constant bright and dark fringes are captured throughout the end. If you compare and see the fringe pattern which is captured in Young single slit experiment and in the double slit experiment, in the double slit experiment, you can see the fringe pattern, it is equal and it is constant throughout the end. But can you see this fringe pattern here? In center, it is the more intensity is there. Central bright band is maximum. It is more, the bandwidth is very large. And if you see the second one, it is reducing, and the third one, it is keep on reducing. Like this, these two sides, the intensity is keep on increasing. Center only the intensity is more. All the other side, the intensity is keep on reducing. That is what you can see it over here. In this diagram also, alternate dark and bright bands, how it is created. Can you see this? This intensity, amplitude is maximum at center. Okay. So amplitude is maximum center, and other areas, it is started decreasing, both up and down. You can see both right and left, the intensities keep on reducing. Okay. So this is central bright band. The intensities keep on decreasing on the other two sides. Okay. So when it comes to diffraction, diffraction is the phenomena by virtue of which the light bend while passing through the slit or an opening. A small opening or slit is there means it will bend and passing through this slit while passing through the slit. And the extent of bending depends upon the diameter of the slit. Diameter, if it is, if it should be very small, that is what we have already discussed here. So both interference means it is two waves are overlapping here, but and diffraction is closely related to each other. It is almost, we can consider that it is a similar thing. Okay, so Young replaced the two slits by single slit in his single slit experiment. Therefore, this experiment is referred as Young single slit experiment. This we have already discussed. When the light passed through one slit, a different type of pattern was observed on the screen. So we have already seen that two slits means different pattern. That is, that pattern is constant throughout the end. But here it is different pattern. The pattern which was observed has a central maximum band. We have already seen that it is a central maximum band. Yes, this is the central maximum band, right? Central maximum band, and which was very wide as compared to the interference pattern. Diffraction pattern is happening now in single slit, and interference pattern is happening in the double slit experiment. So as compared to interference, that is Young's double slit experiment, this central maximum band is very wide. That is what we should understand here. So there were alternate dark and bright bands, and their intensity was decreasing on both the sides. Okay. So central maxima was very wide, whereas the corresponding secondary maxima and minima were reduced in the intensity. Intensity is keep on reducing. This intensity is maximum in the center, and the secondary maxima and the minima is keep on reducing the intensity. Okay. So the change in the pattern was formed due to the diffraction instead of interference. Okay, diffraction instead of interference. Okay. So when it comes to conclusion, what we can come to the conclusion? Young's single slit experiment as a conclusion. The broad central band is captured. Alternate dark and bright bands on either side it is captured. The intensity is decreasing on both sides. This is what we understood. Okay. And let us go to the mathematical expression form of it. Here we are discussing three things. One is central bright band, and secondary maxima, and then minima. These are the three things that we are discussing over here. And here the Fresnel's, that one scientist is there. He defined a certain basic formula to define how it is, the intensity is maximum, how the intensity is minimum. Based on that only, we are going to decide whether the experiment, in this experiment, the slits, that means bright bands, how it is created over here. See this diagram clearly. This is the light from the source. This is the small opening slit over here. In this slit, the top of the slit is named as L, and bottom of the slit is named as N. And in between the slit is bifurcated into each and every points, and the light rays after diffraction, it is making an angle theta. Okay. So this is what it is happening over here. If this happens, this is how the fringe patterns are created. Okay. And first we are going to see the diffraction pattern of maximum. Maximum means it is the incident wavefront is parallel to the plane of a slit. This shows they are in phase with each other, because the phase, can you see here, if it is straight means there is no difference in the phase. They are in the same phase that we can consider over here. Okay. So from the figure, the path difference is NP minus LP. What is NP? This is NP. Okay. And the point is going to reach P. And this is L and P. So what is the path difference in here? NQ is the path difference. I'll have given the explanation in the next slide. Just we can take a look at this. So when it comes to here, this is LP and this is NP. Okay, this is a slit L and N. The same thing I have drawn it here. Can you see it here? This is a slit. This is LP and this is NP. What is the difference between these two LP and NP ray? What is the difference? Path difference. This is the path where it starts, where it ends, and here it starts and here it ends. What is the difference between these two? This NQ, this small portion is the difference, right? Can you see here? This is reaching first, right? So this is starting from here and reaching the same point. So from compared to this line LP, this NP have the extra of this NQ. That is considered as a path difference. So can you see here? One minute. So in this path difference, NP, this is NP minus this LQ, okay, minus this LP. So NP minus LP. Here, LP is equal to QP. Can you understand this? From this point, LP is equal to the point QP over here. Okay, LP is equal to QP. So instead of LP, which is here, I'm substituting the value of QP. Okay, instead of LP, I'm substituting this as QP. Okay, as per the diagram. So what will happen? What is the leftover? What is the leftover? This is NQ is the balance. This is the leftover. So the values comes out to be NQ. And now we are going to take sine theta for this. What is meant by sine theta? So here, for example, in this diagram, L and N, if you draw a straight line over here, this L, N, and this straight line, and this will be considered as the right angle triangle, right? Right angle triangle. In this, if you consider the point N has the angle of 90 degree, okay, this is 90 degree, okay, and the ray is going like this. This makes an angle theta here. Can you see this diagram? This is the theta. Okay, this is the theta value over here. So if this is 90 degree and this is theta, what will be this angle? What will be the angle of LNQ? LNQ angle will be this 90 minus this theta. This is 90 minus theta. This 90 minus theta, okay? So can you see this, the line which is coming from L and joining at Q? This is 90 degree. This is 90 minus theta. If this is 90 degree, so what will be this value? All together should be 180. So this will be 90. This is 90 minus theta. So this angle will be the theta value. I hope you understand this. This same triangle, I have drawn it here. This is theta, this is L, this is N, and this is a point Q. Okay. So if this is theta, what will be the theta value that will consider? Opposite by adjacent. What is opposite here? NQ is the opposite here. What is adjacent? Adjacent is LN. Okay. So NQ by LN, the value that we can consider. What is LN actually? LN is the length of the slit A. Okay. The length of the slit is considered as A over here. So this value comes out to be A. So we are substituting the value of A instead of LN. So sine theta is equal to NQ by LN. LN is equal to A. So if you take the A on the other side, what will happen? NQ is equal to A sine theta. Okay. So NQ is equal to A sine theta. So this is the path difference that we will understand. Understand how the light is making it over here. So at central maxima means the theta should become 0. Theta should become 0 means this rays are going straight. This theta value will become 0. See the diagram on the right side. Okay. So this theta value will become 0 here. 0 means all the lights that are going and hitting the screen will contribute to the brightness. So that in center, the brightness is very, very more. Okay, very, very increasing. So very, very high. That is what we can consider over here. So the path difference is 0 because there is no path difference, because all the rays are going straight. If the theta is equal to 0, so the intensity is maximum. If it is going straight, the path difference is 0, the intensity will be maximum. So all parts of the slit will contribute to the maximum intensity. That is why central maximum bright band is created. So the central maximum occurs occurs at theta is equal to 0. When the angle theta, if it is equal to 0, all the light ray goes straight and hits the screen and the center will become brightness. And how the subsequent secondary minima is there and how the minima, these are all the things which we are going to discuss in the next video. Okay. Thank you.